Mrunmayi will cover now the analysis of a torsional bar subjected to two external loads, and that will be very critical in our understanding of these materials.
Okay, so the problem 2 says a torsional bar is subjected to two external torques. So there is, let's see, there is a 5 Newton meter torque here. There is a 2 Newton meter torque here. Let's see if I can. That's the entire thing. Okay. And there is also a distributed torque. So this torque is distributed over 10 centimeters, so that it's 10 Newton meter per meter. So it's the entire torque. It's like a distribution. So there are like three external torques, one, two, three, and the fourth external torque that the reaction due to the wall will apply. So there are four external torques on this. And what? Okay, so since it's fixed here, the angle of twist at A is 0. So you have to find out the angle of twist everywhere else. I think B and C. And the shear modulus G is given to you. So this is something that you have, the circular rod problem that you must have done in class. So let's look at a quick, before we go into the problem, let's look at a quick formulae that are used. So there is give me a second. Copy the formula. No, not this one. Yeah, this one. Okay, so given the torque, the total length, and the shear modulus G and the torsion coefficient J. So given a rod like this, for example, the total twist in the rod, so twist of this point 2 with respect to point 1 is phi. Then this part is L. There is a torque T applied. So the torque would be something like this. Correct. The torque would be something like this. And TL, GJ. J would be if the if the radius is R, for example, if the diameter is D, then this is pi D4 by 32. Pi D4 by 32. So these are the general formulae that you learned in class. And you derive them very similar to the way you derive this one, just that instead of equilateral triangle, it's a circle. And you would probably go and get the same thing. So you have this, you are equipped with a set of formulae, but this is not simple, right? There are like multiple torsions placed at multiple places on the rod. So it's a little more complex than that, because now the twist here is different, the twist here is different, because the torsion here is different, the T value, right? The T value here is different, it's different here, it's different inside this somewhere, and so on. So you have to find out what the exact thing is going to be. And I'm going to do, give me a second, can I erase this? How can I erase this? Okay, awesome. And the entire shear modulus is the same, but the J value for this and this is going to be different. So it's going to be J1 and J2. Why is the J value different? Because the diameter is different. So the J values are going to be different. So the torques vary. Thankfully, G is not varying, but it could vary. It's possible depending on the structure of the rod. And J1 and J2. So how do you begin to tackle this problem? So let's look at this problem. Before I start, I'm going to show you I'm going to just go through this real quick, the way I use it. So this is a rod, and if I cut here, this is like the x-axis, for example. Sorry, yeah. Is there an axis given? Okay, x and y. Let's see. So there is an x-axis, and there is a y-axis. So where would the z-axis be by the right-hand rule from the x to y? The z-axis would be in this direction. That's correct. From x to y, right? The z-axis. The z-axis would be in that direction. So if you look at this point here, then the normal is in the positive direction. So positive torque is going to be in the positive z direction as well. So the torque, that the t value that I use in the formula is positive in this direction. So it goes like this, comes out of the plane. So it's along the z direction as well. Is the sign convention clear to you? Because you know the formula uses one and you might use the other. So I don't want there to be any confusion. So simply as we discussed in Cartesian coordinate sign convention, right? If the normal is in the positive direction, anything in the positive direction is positive. So the normal for this side is in the positive z direction. So if you look at the torque, if the torque comes out of the plane with the right hand rule, it will be in the positive z direction. So that's positive. That is I find the easiest way to remember what this is. Generally sign conventions don't matter, as I repeat again, because it's what you define. As far as you define it properly, be consistent everywhere, is all good. But since the formula uses a particular sign convention, it's just easier to go with that instead of trying to figure out, is there a negative sign here, is there, if this changes, that changes. Just easier to stick to that. So the t in my case would be positive if it's defined in such a manner. If it's something out of plane on the right side, it'll be on the other side, in the other side of the rod, but sticking to one side. So now we are going to go through this problem, and we are going to use we are going to do this problem, from like we have to divide it into multiple points. Let's I'll show you in a second. So my laptop's a little low on processing power right now. Okay, so there is point A here. Let's name this as point D, and let's name this as point E. So there is A, there is D, E. This part is going to be different. This part is going to be different. So is this. And again, this is different because J is different. Any of the T, L, J, G values L, leave L. Any of the T, G, J values differ. It's a different section to analyze. So this part is going to be different. This A, D, D, E, E, B. Then this part is going to be different because there is a different torque in this and this. I'll explain that. So I'm going to just name this value as F. So it's A, D, E, B, F, C. Okay. So let's do it step by step. First, let's look at what there is going to be a torque here, right? So there's going to be a reaction torque at A. So let's figure out what that torque is. So let's say I set the reaction torque like this. So, okay. So there is a torque here, which is 5. There is a torque here, which is, what is it, 2 Newton meters. This is TA. And this is a little confusing whether in which direction that is pointing. It's going that way. Okay. So it's 10 Newton meter per meter, right? And this step, it's like this. Okay. So do a force balance. This is the FBD, right? Step 1, as was discussed, is the FBD. So what is the FBD? This is the FBD, and you have to find what TA is because that is the only torque you don't know. The rest of the torques you are aware of. So what is TA? TA equals, so it's in the opposite direction. So there's going to be 5 minus 2 plus this. So this is 10 Newton meters into 10 centimeter is what? 0.1 meter? 0.1 meter. And that is 2 plus, that is 1. 0.1. Okay. That is 4 Newton meter. So now you know what TA is. TA is 4 Newton meters. What I'm going to do with this problem instead, I don't want to complicate it, but so what I'm going to do right now itself, just so that we don't have to repeat this calculation again. So the next problem in this series says that what happens if bar has both A and C fixed. That is, instead of the torque 2 Newton meter that is applied at C, it was like a fixed wall. So you don't know what the reaction force there is. So I'm just going to use, instead of 2 Newton meters, I'm just going to use this as TC. So namely phi minus TC plus 1, and that is, so I'm going to just say this is TC, 6 minus TC. Or should we do this? Do we have the time? We can do this again. Okay, let's not. I was planning to, do the two problems together, but let's not get into that. So let's just say TA is 4 Newton meter now. You have the values, you just use the values for now. So you have TA, so you have all the torque. So let's look at so let's go step by step. Let's figure out what the twists are. So part one in this was find the reaction moment at A, which you found. What direction A or torque at A I chose as immaterial because it's not used in any formula. I just needed the value. So as far as you show the direction properly, you show the value properly, you're good to go in any direction it is. So that's done. The reaction moment at A is done. So let's look at the first part. Okay. So let's look at AD. So if you look at AD, if you take the rod, then there is a torque. So it's like this, right? So there is a torque T in this rod. I'm just taking a section, right? I'm taking a cut here in the AD section. So there is a torque T in the AD section because anywhere in this part is going to be the same torque. So I took a cut and the torque is going to be T. And what is my direction chosen here? It's TA like this. And that is 4 Newton meters, right? So there is only a 4 Newton meter torque at A. So T is minus 4 Newton meter. Is this part clear? Yeah. So what I'll do is I'll go one by one. So what I'll do is to give you an overview, I'll find out what happens to the twist in AD. So which will give me phi D with respect to A, right? So phi A is 0. So if phi A is 0, then the entire twist in this, which is phi AD, is basically going to be phi D minus phi A, which is phi D. So that gives me phi D. Then now that I have phi D, I'll go find phi E and so on. I'll do it step by step so that I get to the very end. Because the torques are differing, the coefficients are differing, stuff like that. So let's do step one. So now for the step one, the value of T is minus 4 Newton meter. OD 5 centimeters. So J is what, pi 0.05 the whole raised to 4 by 32, whatever that is. I guess I have the values somewhere, so give me a second. And G is 1 GPa, that is already given. So 1 to 10 raised to 9 pascals. So what is phi AD? So phi AD is T J, so this is J1. For example, the entire thing is J1 and J2 upon TAD. Sorry, that's the correct formula. TL by GJ. My bad. This is GJ1. And L is the entire length, right? So this is 10 centimeters. So it's 0.01 meter. Sorry, 0.1 meter. Wow. Okay. So 0.1 meter. So now you have this, you know by value of this, this, and this. So substituted, get what phi AD is. I'm just going to write the value so that we can go ahead. Give me a second. I have the value somewhere. Phi D, phi A. 0.00065. Okay. So I got a negative value. So it's just convention. And what is the convention I used? So what is the direction of phi? The direction of phi is supposed to be like this, where t and phi. But since I got a negative value, the actual twist physically is in the other direction. That's it. So okay. So now that part is done, we move on to the next part of the same problem. Sorry, I just put, yeah, TAD is this. I plug TAD as this. The torque in AD is going to be same throughout AD. So TAD, I plug that up. Go ahead. So it's just FBD, right? So it's a force balance thing or a movement balance thing. It would have been it would have been positive. Yeah. But I wanted to, follow everything in the formula. So that everywhere I go along the road, my convention still remains the same. Yeah, like this. Yeah. So it's like in the positive Z direction. Yeah. So that, if I had inverted it here, if it was in the other direction, then the twist somewhere else would be in the other direction, and it's, difficult to keep track. So it's easier to keep track of a plus and minus. You just add and subtract. So I get this. So that equals phi d, because phi AD is phi d minus phi A, and phi A is 0. It's fixed. So that directly gives you phi d. So you know what the value of phi d is. Moving on. Yeah. Sorry. No questions. Right? Anybody on Zoom has any questions? Okay. Let's move on. Okay. So moving on to the next part. So the next part is a little complicated, right? So in the entire section DE, so unlike AD, where the torque was the same in the entire section, in DE, the torque changes everywhere, right? So now if I had like a length, say L, take a length L starting from D. So from D, okay. So I know what the torque at D is, right? It's 4 Newton meters. So let's put that here. Give me a second, please. Instead of that, I'm going to do something different. I'm just going to, this seems confusing. So every time I want to find the torque, I'm going to do it from A, because the sign conventions gets confusing. So I have to find the torque at a point. So this is D. I have to find the torque at a point at a distance L away from D. So that it's within the DE section. So let's put this as T. What are all the torques I know? This part here is 10 Newton meter per meter, and that's going to be 10 L. So L is the length, so that's going to be 10 L. And this part, this torque I know, right? So it's from this part. So it's TA equals 4 Newton meter. So it's going to be like this, 4 Newton meters. So now I can find out what T is. So TDE. So TDE equals uh, force balance. It's 10L minus 4. So this torque varies as you go from D to E. Is this part here? It's not the same, right? Because the amount of this torque that comes goes on increasing as you increase L. So it increases as you go from D to E. So we have this. The reason I did it from A is to not be confused with what sign convention torque at D is going to be and stuff like that. So we know what A is. It's a safe bet. So I started from A, but I'm only looking at the D part of the rod right now. So is it clear why the torque D is what it is? So this is a distributed torque, right? This is 10 Newton meter per meter. So for example, if you remember the rod under gravity problem, right? So there was like the stress here was different, the stress here was different amount by depending on the amount of rod you were working with. So similarly, as you go, the amount of torque, distributed torque that you take in into your FBD increases. So the by force or moment balancing, the value of torque changes. But we have an expression of what happens in that entire section. It's going to be 10L minus 4. So let's put that in. So J is going to be J1 just as before, and G is 1 GPa, and L, capital L. So the way I'm going to do it here is, if this point, for example, is some Q, then I'm going to find phi dq. So I'm going to find phi dq, then I'm going to move ahead. So for me to find phi dq, what I'm going to do is I'm going to do an integration, right? From 0 to the entire length, 10 centimeter. There is 10L minus 4 dl upon GJ1. So I'm finding the twist at each and every point. So that is the reason I get that, sorry, phi d e. So Q is like a center point. So I'm trying to find out at what happens at how the twist changes across the entire section D. So that is done by integration, right? Because the torque is changing across the section. So you have to find phi d using an integration method, very similar to what you did there, but now it's like even shorter pieces of rod. That is it.
Excuse me, I have a question really quick.
Yeah, sure, go ahead.
Could you go over the sign convention again? Because in my head, when I look at the torsion on TDE, and then I look at the 4, they're in the same direction to me. So, I don't know. Like if I do the right hand rule, to me, it looks like the 4 should be positive and the 10L should be negative, just based off of like, I don't know, right hand rule. But I don't know. Is that the correct convention, or is there something I'm missing?
Let me check. So TDE. So you have to do a force balance here, right? So you see TDE plus 4. So TDE and 4 are in the same direction, right? Minus 10L
Oh my
equal
gosh,
to,
thank you. Sorry, that makes so much more sense. Thank you.
yeah. So that will give you whatever this is. So when you put that in here, you get an integration. You know how to solve this integration. So you put in the values, you get what phi dE is. So let me see what phi dE is. Um, mm, 0012. One, two. And you know what phi d is, so you can just get phi e by adding this. So phi de is basically phi e minus phi d. So what's that? You have phi d as this, so just add it. I think that will give you minus 0.185, something like this. So do not take my value seriously. There might be some calculation, or try to do it yourself if you can. But try to understand the concept of what I'm going over. So now that you have done 2 of the parts, you know what phi E is. You still don't know what phi B is. So we are still going to go there. So next part is trying to find out what phi B is. Okay. So now that you have this, let's look at a section between E and B. So again, I'm starting from the very start. So there is going to be 4 Newton meters here. And there is going to be this torque in this part. And again, from E to B, the torque is always going to be the same regardless. So at any point between E and B, the torque is going to be the same. So let's say that torque is T, EB. So this is the total torque. What is the total torque? 10 Newton meters into 0.1. So that is 1. So if you use force balance again, then TEB plus 4 minus 1. So TEB equals minus 3. Surprisingly, all the twists are in the opposite direction, but it's all the torques are in the opposite direction. You're getting -3 again and again. So, but it's still a good idea to stick to a single sign convention, I would say. So TEB is -3. Repeat. So you get phi EB is -3 into no integration here. This length, so that is 0.08 upon G is 1 GPa, so 10 raised to 9 into J1. Still the J of this. This is point E. So you get phi E minus phi B. Sorry, the other way around. Phi B minus phi E as some value. You know what phi E is. You now know phi B. So now you have the twist at phi B. So try to understand how you found the twist at phi B. It was not a direct formal application, but it was a formal application in like a smaller step. So now that you have phi B, you can go ahead to find phi C in a very similar fashion. So you take DEF, right? So this point is F. So what happens in BF is you again do the same thing. So I'm just going to do BF real quick. So what happens in section BF is if you look at the rods again. So there is a torque T. Then there is a torque 1 year and there is a torque 4 year. So that's basically T equals 1 minus 4 equals -3. The torque from year to year is actually the same because you don't really have to do it again because there is no torque in between, right? External torque in between. So the entire torque in that region is same. The reason it's a separate part is because the diameter changes. So since the diameter changes, the J value changes. So you cannot use the same formula. So that's why it's a separate section. So now I do phi BF equals -3 into 0.08 upon 10 raised to 9 into now J2. So J2 is basically pi into by 32. Pi d raised to 4 by 32. Right. Can I erase this? This is really bad. Okay. Pi d raised to 4 by 32. So the J change, that's why it's a different section for your calculation. So you do this, you know what pi B is, you get pi F. Now you do the same thing for FC and you can get what the rest of it is. That's it. Go ahead. Mhm. Yeah. So from B to C, it's a different rod, right? So the diameter is different. So there is like a different J. So what I do is for this part, I'm looking at sections, right? So if I look at EB section, then it's a different J. And if I look at BF section, that's a different J. But the twist at B is going to be the same because the rods are connected. So for this one is going to be the 8 centimeter here, this entire L, and this one is going to be the 8 centimeter here, part of it. Look at these two. Yeah, sorry. So this 8 and this 8. This is EB and this is BF. This point is F. No, it's not all the way to C. I'm still doing it step by step because I cannot do it all the way to C because there's this external torque in between. So the torque from F to C would be different. No. This point is somewhere between F and B. It's just the BF section I'm looking at. Yeah. Sorry. So because this part is only up till F, I get your confusion. So this rod will go up till C here. I'm just looking at the rod up till F. So that external rod doesn't come into question just yet. This external torque. Because it's beyond F, right? If I make a cut here, for example, the external torque is not going to come in question. Okay, so the cut you take one before F. So I'm just looking at the BF section. I'm not looking at the entire BC section.
So why are T and external torque not the same? They're like, you're taking the torque right before the side is applied?
right before the 5 is applied, yeah. Which is a positive. I mean, yeah, that's a 5 Newton meters here. It's in that direction.
So it's like at that point another 5 is added on.
So give me a second. So what happens at a point beyond F is so say you take a cut between F and C, for example. So this point is F. So at F, there is a torque like this, right? Phi. This is the distributed torque 1, and there is 4 here. So at this point, there is a torque T between F and C. So now if you do the force balance, you should get T equals -2. So you see that if you do it from the force balance from any end, if you do it from this end, for example, if I take a cut here and I look at the rod like this, okay, so there is C here and there is a torque T in this direction, T. So if I make a cut here and instead of looking at this part, now I look at this part. So this is 2 Newton meter, right? The external torque. So this is going to be 2 Newton meter here.
I think like using colors
But
we're not at that. Like we're taking a full
correct.
But then really we're not something.
We are infinitely close. That's correct. So the torque is at F, but we are not looking at we are looking at the part before that torque.
And it's close enough that it's like
yeah, it's like saying that if, for example, if there is a force P here in a beam, for example, and if you take a cut here and just look at this section, then there is no external force on that section. So you can come infinitely closer to P, but there is no external force there. So something like that. So if you look at a section, this is a very mathematical concept per se, because you cannot put a force at a single point. It is generally distributed. So you cannot just say you can just say B to F. I'm just there is no torque there, because at F is a very weird concept. But for the sake of our mathematical computations, you say that you go infinitely close to F, there is no torque. As soon as you cross F, or as soon as you are at F, for example, there is going to be a torque. So that's it.
Kind of like instead of being like TBF, it would be like TBF minus, so it's like right before F. I don't know if that is like a notation I'm familiar with, but it's kind of like right before.
Kind of, yeah. TBF minus, sorry. Yeah, that makes sense. That's correct. So that's the same thing you did in all of this, right? So when you were in this section, you did not account for any of this torque because it's after that point.
Okay.
Yeah. Right. So is this part clear to everybody? Okay. So if you see here, this might be a little confusing, but I still want to go over it, is that when you found the T using this, you got it to be a -2 value, and here you got it to be a +2 value. The sign convention is still the same, right? Negative direction, negative normal direction, the sign convention still remains the same. But it is just different in the way you see it, because at this point, this T is the force applied by this part on this section. So it's in this direction. And it's going to be equal and opposite on the other part, right? So if you look at the directions, those make sense. Do those make sense? Is this part clear? Why the signs are different? In this, right? On the bottom part you're talking about? Here? Oh, I think I did it wrong, is it? Oh, yeah. Sorry. This is +2. Oh, well, that makes sense. But I'm asking you to look at the directions. So the direction of this T, if you look at this rod, is in this direction. This is 2 Newton meter, and that is in the opposite direction. That is, you realize why the two T's are in the opposite direction, right? They're at the same point, but in the opposite direction, because did the brightness decrease? Can you still see it, or can you not see it? Give me a second. I think, okay. So I don't want to confuse you, but so I want to make clear you understand that there is this equal and opposite torque on the two sides. So this is the T here and this is the T here. So there I tried to calculate the same T using two different parts of the row.
Okay, so why is the 6 minus 4 positive 2 if there's more torque in the opposite direction of T, you can make it minus? Sorry, that didn't make sense.
So no, so for force balance, it's going to be 4 plus T equals 1 plus 5, right? So it's going to be T plus 4 minus 1 minus 5 equals 0. So that was my bad. I made that calculation mistake before. So it's T plus 4 minus 1 minus 5 equals 0. So T is plus 2. So the torque is equal and opposite because this torque is applied by this section on this rod and the other way around. Equal and opposite reaction, Newton's law, right? But I wanted to show you how you can do it either way, right? Because here, if you want to do FC, right? So now you can do FC equals TL by GJ, and you can use the same T because the value of the T's remains same. So you can put it in the formula, it's going to be the same. The direction is different in the way you look at the problem. But it's always still going to be phi C minus phi L. So you don't know phi C, right? You know phi F, but you can use either way to do it. You can use the entire rod on the left or you can use the entire rod on the right. And it's still going to be the same. Is this part clear? Because the value of T in the formula that you put is still going to remain the same. Sign and all, everything. You'll still use the value of T you get. So you will still use, either way you do it, right? You see that the sign remains the same. So when you put it in the formula, it's still going to work. But don't look at it like, when you do it from this end, this still remains the same. It's phi C minus phi F. So there's no confusion. The formula remains exactly the same either way you do it. So just you have to take care of the sign convention. If you maintain the same sign convention, the formula remains the same. That's it. So the sign convention here is the normal is in the positive direction. So this is in the positive direction. The sign convention here is the normal is in the negative direction. So this is in the negative direction as well, along the normal. Torque is always along the normal. Is that clear? If you follow that, then the formula remains exactly the same. There is no sign change in the formula. So why is that important is for a problem like this, right? So this is the same problem as we did before.